Okay, so and there's a lot of math involved, and I don't want to go into it. So I want to give you the results of what they consider the BET model. If I go back to my math page, what it is like the Langmuir model. So you look at all this equation, okay. So but don't worry so much about it. What I like you to compare. This is my Langmuir model. Okay, my theta is partial pressure. 1 plus my partial pressure, right? My mole fraction times total pressure is my partial pressure. Look at this BET model, right? BET model can be written as something like this. It's kind of like A divided by B, B plus A. Very similar to it. And it's quite similar to this guy, because I can write, I can write chi sub p 1 plus chi sub p 1, right? So if I take A to be my chi sub, A is chi times p, and 1 is my B, right? You can see the symmetry between this. If I take A to be chi p and B is equal to 1, I got back the Langmuir model, right? So that's exactly what it is. So I want you to just think about it like that in terms of analogy between the BET model. They have the same form. Langmuir model and BET model have the same form. They have this same form here, except in Langmuir model, A is equal to partial pressure and B is equal to 1. Okay? Whereas in the case of BET model, what is A? A is K times P divided by Q. It's kind of like chi P. Not a big deal. It's like partial pressure. This whole term is like partial pressure. But B here is still 1 as in Langmuir model. You have a correction to 1. And the correction to 1 depends on my pressure. Okay, so that's all, right? So that's it. So this, how is this correction go? Correction, this 1 minus some correction term, and this correction term depends on something called Q. And Q is related to N naught, which is the variable side, divided by the mean stay time of the double layer. Okay, so this tau A2, you can think of it of service lifetime for all other patches. Just make it simple. We ignore triple and quadruple. Just think of it multiple, right? This tau of A2 are related to multiple layers. So it's quite reasonable, right? This BET model and Langmuir model are really, they converge to each other, because if you think of B here, which ought to be 1 in the case of Langmuir model, but in the case of BET model, it depends on how many doubles or triples you have. Are there multiple patches that you have in terms of mean state lifetime? Okay, so that's it. So that's the kind of thing that I like you to know qualitatively in terms of BET model, with some feel for the mathematics involved, and the feel related to this is the correction. This B really just have a correction inside, which is P divided by Q, and Q is related to the service lifetime of all other patches related to these multiple patches that you have in here. Okay. And so if you do that, what you got is that you have a different absorption isotherm, right? If you plot the Q, this Q here, N naught divided by beta T naught, tau is the service lifetime for all other patches, you may get a different looking form, and this is the different looking form. Absorption isotherm that you see like this. And they look rather different compared to my thing that you see, right? This is my conversion to 1, and here I don't have a conversion to 1. It depends on my Q and my limiting pressure. Okay, So if Q is greater than my limiting pressure, it goes infinitely like this. And you can see my coverage, instead of curving towards 1, it exploded to infinity like this. Okay, so the form look very different between the BET, and that is good because in the case of PC absorption, there should be no limit on how much coverage you have. Okay, because there's a limiting pressure to build up this coverage. Your coverage should go to infinity, and this can all be done. You can get all of that from this equation here, and if you plot it, you will get this kind of plot that you see. Okay, so that's quite nice. I think other than all these mathematics, as long as we appreciate the physics behind this, it will be good that we know a little bit about this. Okay, so next thing, just a simple thing, I'd like to talk a little bit about how you learn about these absorption and migration. And one of the common techniques that you probe these, experimental technique to probe this, is thermal desorption. So essentially a simple idea that you heat up your surface and look at what comes up. That's essentially what thermal desorption spectroscopy is. The common technique to look at absorption behavior is thermal desorption spectrometry or temperature program desorption. Depending on how you call this is a common technique. One of the interesting things that you have to be aware is that desorption is not equivalent to absorption, right? And this is a common mistake. Sometimes people think absorption is exactly the same as desorption. They are not, because something could happen in between, which is the diffusion and surface chemistry could occur on the surface. And so therefore, if you're talking about, if you're thinking, oh, if I absorb something, I heat it up, that same thing would come out. That's not true. Unless that thing is not interacting like a noble atom or something like that. But if it's not a noble atom, like CO or something like this, then you would expect in the process of moving around on the surface, it may see other things, other atoms, and reaction could occur. So what you see in the desorption process may not totally reflect the absorption process, because the missing part is surface diffusion and surface chemistry in the middle part. Okay, remember this very simple, qualitative, but powerful picture that we have, right? We are equating, right? We are trying to say this is equal to this, but that's not true, because what is missing is here, is the middle part, diffusion and chemistry part, that something could occur. So what you detect here could reflect both this and this, both of these processes. So that's a carrot that people should be aware to keep in mind, that don't fall into the trap of thinking they are exactly the same. But in some cases, like if you're talking about non-interacting material, then you can think of them to be the same. Okay? So I'm going to stop here today. We have teaching evaluation to do today. So, and next day I'm going to talk about the process of looking at these desorption, and then we'll talk a little bit about fun thing about chemistry and catalysis with this. Okay. So the